Hi, and welcome to this next video in the series on differentiation. We're continuing on with our journey into differentiation, and specifically we've been looking a lot at chain rule stuff, and we're going to have a look at parametric curves. And again, would you believe this is a chain rule issue again, as most things are. So we're going to have a look at how we find the gradient of a parametric curve. So there we go. We've got a curve that's defined parametrically. It's x equals 4t plus 3, y equals 4t plus 8. Plus 5 over 2t. Okay, so find the value of dy dx at the point where t equals 2. Now you'll notice we want dy dx with change in y with change in x, but these things are defined in terms of t, so what we're actually going to end up with is dy dx in terms of t, and we're going to get at it this way. So dy dx is dy dt times by dt dx. You'll notice that what we've had to do, kind of effectively what we're going to get is this upside down version here, dt dx. From this one here, we'd get dx dt, but for chain rule to work, we need dy on the top, dx on the bottom, and dt's cancel. So we're going to have to flip the dx dt, but we know from previous videos that we can do that. So let's just crack on. We'll go. Let's start off with dy dt. So I've written the 5 over 2t as t to the minus 1, and now we'll differentiate it. There we go. Now we've got x equals 4t plus 3, so we're differentiating x with respect to t, so that's going to give us dx dt. So let's do that, and dx dt is just 4. The one we want is dt dx, so what we're going to need to do is flip it upside down, as we know we can, so dt dx is a quarter. So therefore we've now got dy dx is going to be dy dt, this bit up here, times by dt dx, which is the quarter, and then when t equals 2, we just put t equals 2 into here, and we end up with 27 over 8 coming from the bracket, times by a quarter, which is 27 over 32. You'll notice I wasn't being asked specifically for an expression for dy dx, so I didn't really worry too much about tidying this up. I just subbed t straight in. And there we go, so there's part A sorted. And so on we go to part B. Part B says, find the coordinates of the point where the tangent to the curve at P cuts the x-axis. So I need the tangent to the curve at P where t equals 2. So I've already got the gradient from part A, so I just need the x and the y coordinate. They're clearly going to come from my definitions up here. So when t equals 2, x is 11, coming from that one. And when t equals 2, coming from this one over here, y, as it turns out, 69 over 4. So now I've got enough of my y minus y1 equals mx minus x1. Bang in the values. There we go. Now we're not specifically being asked for the equation of the line. We're being asked for the point where the tangent cuts the x-axis. So it's going to cut the x-axis when y equals 0. So let's plug that in. So we've now got that. Now I've got an equation to solve. And once I've tidied all that up, I haven't done the solving there because you're obviously more than good enough at dealing with those ones for yourselves now. So that gives us my x coordinate of the answer we're after, minus 85 over 9. Okay, so that one was reasonably straightforward. Let's go on to one that's a little bit more tricky, and it involves some trig. So what we've got is our curve up here, and it's defined parametrically 3 cos 2t for x and y equals 2 sin t. And first of all, we've got to show that. We've got to show dy dx is minus 1/6 cosec t. As ever with show that questions in the exam, you've got to be absolutely clear on where everything is coming from. So we've got to show each step of our working. So here we go. Let's start off with dy dx is dy dt by dt dx. So y equals 2 sin t, so that gives us dy dt 2 cos t. We've got x equals 3 cos 2t. Remember, differentiate cos, you get minus sign, and this one as well, we've got to bring the 2 out of there. So we get dx dt equals minus 6 sin 2t. And we want dt dx, so we've got to flip that one upside down. So that gives us dt dx is 1 over minus 6 sin 2t. Right, so we've got to work towards cosec, so let's put them all together using chain rule. So there we go. Now, what can we do with this one? Well, again, we're looking for this as cosec t, so just t, whereas down here I've got sine 2t, so we're going to have to deal with that. So subbing in sine 2t equals 2 sine t cos t would be the way to go there. There we go. Bit of cancelling. The causes will cancel. The 2's will cancel. Now we're getting somewhere near where we need to go. So we've got 1 over minus 6 sine t, and 1 over sine is cosec. So there's the result that we're after. Job's a good one. Right, that's part A done. Let's crack on with part B. Find the equation of the normal to the curve at P when t is pi over 6. So first things first, let's figure out where P is. So when t is pi over 6, going into our definition for x, that gives us 3 over 2. And y, let's just stick pi over 6 into that one, and you end up with y equals 1. So we've got our point P, which is at 3 over 2, 1, and the blue line that's appeared there on the graph, that's the equation of the normal that we're after. So clearly, in order to find the gradient of the blue line, I'm going to first of all need the gradient of the curve. So imagine we've got a tangent going down there, and we'll need the gradient of that. So we're going to need dy dx. There we had dy dx is minus 1 over 6 cosec t when t is pi over 6. So plug that in, and I've written that back using 1 over sine, because that's what I'm going to put into my calculator. And out of there comes a gradient of minus 1/3. So the gradient of the curve at P is minus 1/3, which means the gradient of my blue line, the gradient of my normal, is going to be 3. And there we go, y minus y1 equals 1, x minus x1. Put in all the values, and there we go. And again, it doesn't tell us what format we need, so I'm just going to leave it like that. I don't need to do anything more with it. Okay, on we go to part C. And part C, we wanted the exact coordinates of Q, and from the question, Q was the point where my normal intersected the curve for a second time. So what we're going to have to do is work with my equation there and my equation for the curve, where it's going to solve them simultaneously. And to do that, what we're going to do is take our our definitions for x, our definition for y, and we're going to plug those into our equation of the normal. So let's take that and plug that one in there. Let's take that and plug that one in there. And so now we've got an equation in terms of t. Again, the problem that we've got is this is in terms of 2t, so I'm going to have to get rid of that. The way to go around that is, again, if you know it, fine. If not, do a bit of scribbling over on the right side of your page. So cos 2t is cos squared minus sine squared. Let's replace the cos squared with a 1 minus sine squared. There we go. So cos 2t is 1 minus 2 sine squared t. So that's what I'm going to substitute in my blue bit here. So we get that. So now what I've got is an equation just in terms of sine. Multiply out the brackets. Turns out it's a quadratic. So let's do some tidying up. And there we go. So again, we've kind of moved the all this stuff over here on the left has been moved over. So on the right has been moved over to the left. And then I've times through by 2 as well to get rid of the fraction. Hopefully that's all fairly obvious. Right, so now what we're going to do is solve that. So factorize, equation solver, whatever you want to use. You end up with sine t equals a half. Now that's what we had previously, because that gives us t equals pi over 6. So that's one we already knew about. So that gives us our value, our point P. The one we're interested in, what is the value of t for point Q? So that's going to come from the other solution from our quadratic. And that turns out to be minus 11 over 18. So now what we've got to do is work out the exact coordinates of Q. Now, I'm not going to go as far as trying to work out the actual value of t, because it'll be a great big long decimal. It's probably a little bit easier just to work with this value of sine t equals minus 11 over 18, because if we go back to our definitions up here, we've got y equals 2 sine t. Well, I already know what sine t is, so I can use that. Over here, x equals 3 cos 2t, and we already had x equals cos 2t, we said was 3, 1 minus 2 sine squared. So now, we know sine t is minus 11 over 18, so we need the square of minus 11 over 18 in that bit there. In it goes, and so that gives you an x coordinate, which is that value, which is a bit of a shocker of a fraction, but okay, fair dues. And then the y1 is a little bit simpler. There it is. 2 times minus 11 over 18, and so therefore there's my coordinates for Q, and there we go, that's all sorted.